The practice of solving right triangles can help us in many real-life applications. In section 1.5.4, we're specifically going to consider the angles of elevation and depression. Here's the definition. Starting with the angle of elevation, this one's pretty straightforward. The angle of elevation alpha for a point above a horizontal line is formed by the horizontal line and the observer's line of sight through the point. So, for example, if we're looking at the very top of the Empire State Building, then the angle of elevation to that point is going to be formed from this horizontal with the terminal side of the angle representing our line of sight to the top of that building. So that's the angle of elevation. On the other hand, the angle of depression, a little less straightforward. The angle of depression, beta, for a point below a horizontal line, is the angle formed by a horizontal line and the observer's line of sight through the point. So notice this is the angle of depression. Make sure that when you're working your application problems that you don't accidentally think of this as the angle of depression. Now, the interesting thing, if we look here, we've got two horizontal lines cut by a transverse line, which means we are dealing with a couple of alternate interior angles. So the angle of elevation here is equal to the angle of depression here. With these principles and definitions in mind, let's work example 6. Says the angle of elevation of the top of a water tower from point A on the ground is 19.9 degrees. So here's point A, the angle of elevation between the horizontal represented by the ground and our line of sight to the top of the water tower, that's 19.9 degrees. If we walk 50 feet closer to point B and we remeasure the angle of elevation, we're going to find it to be 21.8 degrees. Now here's a good question. What is the height of the tower? Now we're going to be able to measure the height of this tower using mathematics alone without having to actually physically measure the height of that very tall tower, which is very convenient. I mean, the mathematics is convenient. Not measuring the tower physically is convenient, right? So in this problem, we actually have taken 3 measurements. The angle of elevation here, that's pretty convenient to do. The angle of elevation here, also convenient, and this distance. From those 3 measurements, we will be able to find the height of the water tower. So let's get started. First of all, recognize there is a right angle implied between the tower and the ground. So we're working with a couple of right triangles. Let's work with, first of all, triangle BC, and we'll just call this point D for convenience. So working with that first triangle, BCD, notice we can write an equation using SOHCAHTOA. So we can say, because we know the opposite and the adjacent, or at least we've represented it with variables, tangent, that's TOA, right? Tangent of 21.8 degrees equals opposite over adjacent. So I have here one equation in 2 variables. In order to solve for 2 unknowns, we need 2 equations. So we need to write a second equation in x and y. So for our second equation, we will consider the larger triangle here, triangle ACD. It is also a right triangle, but it has an acute angle of 19.9 degrees. Also notice that the horizontal segment has this unknown quantity x plus the 50 feet that we measured. So when we apply SOHCAHTOA, TOA, opposite over adjacent, tangent of the angle 19.9 degrees is equal to the opposite side over the adjacent. The adjacent is 50 plus x. So now we have a system of 2 equations and 2 variables. We can solve this system by substitution. Keep in mind we're most interested in solving for y. So let's isolate y in that first equation. Notice we can multiply both sides by x. We get x tangent of 21.8 degrees equals y. So at this point, I could take this information here, plug it into the other equation for y, and I would have an equation in one variable that I could solve. But I'd be solving for x, and even though I could use x to find y, I want to set it up to where I can solve for y the first time around. So let's manipulate this first equation one more time and isolate x. Dividing both sides by tangent of 21.8, we can see that x equals y divided by tangent of 21.8 degrees. So now I'm going to take this information and plug it in for x right here. Let's see what that looks like. We have tangent of 19.9 degrees equals y over 50 plus our new y, which is y over tangent of 21.8 degrees. So we have a pretty complicated equation here. We've got a complex fraction in the bottom, but our equation is in terms of y, and that's what we're looking for. So next we need to solve this equation for y. The first thing I want to do is clear that fraction. To clear the fraction, I'm going to multiply both sides by the denominator of this big fraction. And to see the portions of the fraction clearly, I'm going to write it over 1, okay? And on this side, I'm just going to put it in a big set of parentheses, 50 plus y divided by tangent of 21.8 degrees. Over here on the right side of the equation, you can see that the entire denominator is going to cancel, and the only thing left on the right side is y. Now on the left side, we've got two terms times a single term. So let's break up these parentheses with the distributive property. So we're going to end up with 50 times tangent of 19.9 degrees plus y times tangent of 19.9 degrees divided by tangent of 21.8 degrees. Our goal is to solve for y, and at this point we've got a y on both sides of the equation. So it would be convenient for us to combine those y's. So we're going to subtract this term from both sides. When we subtract it from the left side, it's going to cancel, and then it's going to appear over there on the right side. So we get 50 tangent of 19.9 degrees equals y minus this big term, y tangent of 19.9 degrees divided by tangent of 21.8 degrees. Now, by the way, in case you were thinking this, do not be tempted to cancel those tangents. Okay, I'm going to put big red dirty words on your paper if you do that. No, I'm just kidding. Don't cancel those tangents. They're not factors, they're functions. We can't cancel functions. Just like you can't cancel natural logs, don't cancel those tangents. So in case you were tempted to do that, I'm glad I caught you early. Working on the right side, we've got two terms that contain y. They are like terms, but they're not very compatible. So what we need to do is factor the greatest common factor of y out of both of those terms. So our left side's going to hang out for just a minute. I'm going to wait to evaluate that at the very end of the problem. And on our right side, we're going to factor out a y. Okay, if we take a y out of the first term, that leaves behind a 1. And then we have this quotient. Tangent of 19.9 degrees divided by tangent of 21.8 degrees. So the last step is to isolate y, and we can isolate y by dividing both sides by that big factor on the right. So both sides will be divided by 1 minus tangent of 19.9 degrees divided by tangent of 21.8 degrees. I'm about out of room. How about y'all? I bet you are as well. The further you progress into your mathematics, the smaller your handwriting will become. So by the time you get to differential equations, you're going to be writing really tiny and precisely. Don't say I didn't warn you. Okay, y is isolated on the right. I'm going to sneak over here and use this space. So we have y equals 50 tangent of 19.9 degrees divided by 1 minus tangent of 19.9 degrees divided by tangent of 21.8 degrees. That's our exact solution. By the way, that's the height of the tower in feet, but it doesn't make a lot of sense to us, so it will be prudent to go ahead and approximate this with our calculator. So be absolutely sure that you are in degree mode, and we're going to type this in all in one step. Now, another thing that's important here is to recognize that we have an operation, a difference in that denominator. So when I type this into my calculator, I'm going to need an additional set of parentheses to set off that denominator. And I do recommend typing this in one step. You don't want to type in the numerator and approximate that, type in the denominator and approximate. You're going to get too much rounding error. You're going to accrue it over time. So round once at the end of the problem, okay? So I've opened parentheses for my denominator. I have 1 minus tangent of 19.9. Make sure you close parentheses for each argument of your trig function. Your calculator's automatically going to open them. Make sure you close it. Okay, I'm also going to close parentheses for my denominator here, and we end up with 190.627. The problem did not indicate the decimal place to which we should round, so let's just round to the nearest foot and call it 191 feet. So, big conclusion, the tower, whose height was given by y, is 191 feet tall. The tower is 191 feet tall. We were able to determine its height without physically having to climb the tower. For those of you that are commuting between Amarillo and Canyon, maybe you're concurrently going to WT, there's a big water tower between Amarillo and Canyon. It looks just like this, and it has the name Canyon on it. My son is named Canyon, and so he gets really excited when we drive by that water tower. It's pretty cool. So if you drive by that water tower, think about me and think about trigonometry. Now let's do another example. This one's much easier, by the way, so don't panic. This one's very straightforward. It says the angle of elevation of a pedestrian crosswalk over a busy highway is 8.34 degrees. So we've got our horizontal that's going to go across the street, the 2 lanes of this busy highway. The elevation angle here is 8.34 degrees. And notice we've got the same angle of elevation on both sides. So it looks like we're dealing with an isosceles triangle here. If the distance between the ends of the crosswalk measured on the ground is 342 feet, I don't know where that came from, 342 feet, then what is the height h of the crosswalk at the center? Now, since we are dealing with an isosceles triangle here, then this altitude is going to bisect this bottom segment. So we know that the 2 halves of the 2 lanes have equal distances across. 342 divided by 2 is 171. So 171 feet on this side and 171 feet across on this side. Our goal is to find the height h. So notice we do have a right triangle over here on the right side that we could make use of to answer the question. Notice the angle we know is opposite the side h and adjacent to the side 171. So we know opposite and adjacent, which means we know tangent. TOA is tangent. So tangent of 8.34 degrees equals opposite side h over adjacent side 171. We can multiply both sides by 171, and that will give us h. Much easier than the last problem, right? Let's type that in. 171 times tangent of 8.34. My calculator is in degree mode. So the height of the crosswalk is 25.07. And we're going to round to the nearest tenth, so let's call that 25.1. The height is approximately 25.1. So let's make our formal conclusion. The height of the crosswalk at the center is 25.1, and that's measured in feet. So this is the part in your engineering problem where you have to turn around and write the report and submit it to the boss, right? Our report, the height of the crosswalk at the center is 25.1 feet. So in this section, we learned how to solve right triangles using SOHCAHTOA. We learned a little bit about inverse trigonometric functions, and we practiced solving triangles and looked at angles of elevation and depression as an application of solving triangles. So that completes section 1.5.